Yes, welcome to the 5th episode of the Corona series. So I will explain a little bit about stochastic individually based SIR models, what I call these. I will restrict, as I already indicated before, to a very particular one, a model where you suppose that as an individual, at a random time, tau I, you get infected, and then after an initial period, which is denoted by A0, the incubation time, you become infectious with a constant rate, in this case, up to the point that is called Bj, which is another random time for you when you are quarantined. And when we are trying to model such a process in continuous time, I already told you that what you get is, again, a rate of change equality, so an ordinary differential equation, but it is one for a probability. It is not for the event, it is for the probability that you get an ordinary differential equation. That is a parameter, real parameter, continuous parameter. But of course, the process itself is a discrete process. So you have a certain time for J when you are infected. Then at the time tau J plus A0, you start being infectious, and you are removed with a certain probability at another random time, and this is called Bj. You are removed usually by quarantining. In this process, in the corona process, epidemiologically, the mortality is so low that it doesn't play any role. Now, as I'm saying, we have this rate of change law for the infection time, and we have a similar rate of change law for the quarantining time. And I assume that, of course, the probability that Bj is larger than A0 is equal to 1. But then at this point A0, it can be that you are detected. And you are, if you are detected, and there is a probability rate which is given by this delta, then you are removed, put in quarantine. Such a process itself, obviously, such a process is well defined, and the main kind of thing to why it is well defined is, I would say, that the probability that two of these events for one individual or another individual occur at exactly the same time is 0. So you will have a process, and the picture of this process, I'm giving that only in terms of this one here. This means the number of individuals J which are infectious, and that is the condition for being infectious. Now, when you look at this number in time, so this should be, the arrow should be time, then this is, of course, just what I have here. It is just a discrete process, yeah? This 1 over n times the number. So the number is a natural number. You divide by n. So this process is a jump process. The jumps occur at random times. So this is a piecewise constant function. And the jumps are all of order 1, not only of order 1 over n, they are of size 1 over n. So this can go down or up by 1 over n. According to this, goes up by the process tau J. For one individual, goes down by the process Bj for another individual, let's say. So it's a kind of it's a piecewise constant process, but it is the jumps are very small. if n is large. And that is the reason, together with the fact that the only, what I would call the only coupling between the process for one individual and the other individual is via this kind of average number. That is the reason why for large n, you will approximate actually a deterministic process. That's nothing else but the law of large numbers, which we have here. And the deterministic process that we are approximating, I already told you what it is. It's just a kind of SIR process, but with another parameter A, that is we sometimes call it the age structure of the population of infectious individuals. So what we have here is that the change of the rate or percentage of susceptibles in this population, so I do it here only for one homogeneous population, is equal to the rate at which individuals get infected, because I mean afterwards they are of course no longer susceptible, and this rate again is the product of two factors, just like up there. It's the product of the available kind of susceptible population and a weighted, I would call, we'll explain this later, and an integral term in terms of all the infectious individuals which are infectious, so A is larger than A0, and you just take, well, I mean, the integral, that's like the sum which you have there, this, what I call this integral A0 to d I of ta. So this thing is actually 1 over n, or is the limit of this 1 over n and the number which you see there. So it is actually this kind of what I will call, it's a kind of scalar parameter, because I mean it is only via this mean that the different processes interact with each other. And because you are only interacting via a mean, that is also usually called a mean field model in statistical physics. Now, what's the reason why I'm claiming it's, let's say, it's not quite so difficult to show that, and what does it mean? The result is also, of course, an important point, that the process which we had here, so this process is actually converging to a solution of this deterministic, actually it is a PDE, because you have here two partial derivatives there, the partial derivative in t and the partial derivative in the parameter a, which is just the time since infection for each individual. So why is that still possible? To prove what is the main reason, or I could also say what's the main tool there. The main tool is, of course, that you have to see in this kind of equation, how is the evolution of this? Now, it's not a parameter I of t, but it's now a curve I of ta, right? So a is the age structure parameter. So what's the evolution of this curve which we have there? And I tried to draw this in this diagram. So the diagram tells you, so these kind of broken lines there, they are what we call the characteristics of this linear differential equation here, dt plus dA I of dA, because I mean this dt plus dA just means the derivative with respect to the parameter t plus a. That's the characteristic of this equation. Now, when you look at such a simple type of equation, then you can solve it more or less explicitly, so you know exactly what the point here, which is connected to the point here, actually what the value of I of TA is here, if you know it here, because you solve explicitly this differential equation there along the characteristic. So basically you have this kind of, I will call it kind of transport there of your data. Of course, you are only interested up to the time d, so I'm only transporting what was here at the time, the data at up to the level d minus t, if this is the, or d minus delta t, if this is the time interval. But then I'm also, of course, changing by this integral term here. So by the I of t0, I'm also changing data. So here there are new data coming up, and the influence of these data, that's what we see here. So we have the same kind of characteristics, but of course what you see is the influence is only over a very short interval that we have there. So it is not very large. That means that we have actually, that there are two ways to look at this. You can look at it as a partial differential equation in these two parameters, d and t and a, sorry, t and a, or you can look at it also as something which we call an ordinary differential equation in the space of curves. So the space of curves are these I of t, a, where a is a parameter which you have there. And the type of the way, for instance, that you solve such an equation is, how should I say, with a very basic kind of tool that is just the Banach fixed point theorem, or we call it in ordinary differential equations. This is its application is called the Picard-Lindlöf theorem. And the point now is, why is it not so difficult to go from this equation to this equation? If you have an integral operator to which you want to apply the Banach fixed point theorem, then you can always estimate the distance between any, what I said, any curve in this case, and the corresponding solution, that is the fixed point of your integral equation. You can estimate it by the deviation from being a fixed point of your operator applied to d. So it is much simpler to deal with such an equation in that way than it would be to deal with a very general, not mean field type process here. So basically what this then says in the end is, it's not only true that somehow for large n you will converge to this equation, but actually you also have a kind of something like a quantitative, not very good, but something like a quantitative estimate, which tells you that whenever the process is such that it doesn't have to have exactly this kind of behavior, but if the process is such that if you can show for the process that if the process is plugged, the solution, the probability that the process itself plugged into the operator gives you a deviation from the fixed point equation if that probability is small, then it tells you that with a small probability, you will be far away from the fixed point equation. So it is a kind of much, how shall I say, the applicability of this theorem is, or of this method, is not really limited only to the case n going to infinity, because you could always ask yourself how big has n to be. But as I'm saying, I mean, actually n doesn't have to be too large in order to be able to approximate the empirical distribution of this process just by the solution to this kind of equation, which we call a delay differential equation. Thank you very much.